Hello, everyone, and welcome to our presentation for project Milestone 2 on pedestrian crossing intention prediction. This is Mohamed Noureldin with Hashem Abdelfattah.
So our problem statement is that self-driving cars are getting popular in recent years. And one of the main challenges that face autonomous driving cars is the predicting of that whether a pedestrian is willing to cross the road or not. So the ability to predict this intention is necessary to reach stage 4 of autonomous vehicles, where vehicles can fully drive themselves without any human intervention. And this task of predicting the intention of pedestrians is very difficult, especially in urban areas like Egypt.
Okay, so let us first recap our original model and how we are improving on it. Our original model is from a paper called Predicting a Pedestrian Crossing Intention with Feature Fusion and Spatiotemporal Attention. It was published in 2022, so it is very recent. This model proposed a unique or a better solution by instead of just focusing on a human pose, for example, but instead of fusing multiple features together. These multiple features are included in non-vision features and vision features, as can be seen in the picture here of the non-vision branch and vision branch. The non-vision branch includes stuff like the vehicle speed, like the bounding box and pose key points, being fused together into a hierarchical or different order, where the last in order is the more important to the model. For example, here the vehicle speed is the most important or critical info. For the local context, we are focusing on the person himself and his poses, and the global context is the things surrounding him. Our model uses CNNs and RNNs. The RNN that our model uses was of GRU or gated recurrent units. Our model reuses pre-trained VGG19 model in its architecture that was pre-trained on ImageNet. It takes a sequence of images extracted from a video where their dimensions are 16 by 224 by 224 by 3. The model contains 256 hidden units of GRU. It results in an accuracy equal to 83% and uses average pooling in its architecture and an L2 regularizer with some dropout layers included in the middle.
So the improvements that we have achieved from Milestone 1, that after training the model, we have achieved a better accuracy by replacing GRU with the LSTM, and we increased the accuracy by 5.5%. We also tried to use average pooling instead of max pooling, but it reduced the accuracy, so we stuck to the average pooling in our model. And here are the proposed updates in this milestone: adding a validation dataset to check overfitting, replacing L2 with L1 regularizers and also with L2 L1 regularizer. We also tried another Deep Lab V3 model version, and we changed the optimizer from Adam to SGD and RMS prop to Caesar results.
Okay, let us first explain why did we decide to use the validation dataset in our model. Last time in our first milestone, we did not have a complete way of measuring overfitting or underfitting of our model. We only had the accuracy and the loss, but only the training loss and the testing accuracy and testing loss. But we did not have, like in our assignments, how the validation accuracy and validation loss changes over epochs. So we decided to include a validation subset or a validation dataset in our model so that we can see how the validation accuracy and validation loss changes over the number of epochs. Firstly, when we try to include this caused us a problem when generating initial materials and weights that the model uses, for example, the mask CNNs, weights and stuff like this. So we had to decrease the batch size from 2 to 1, which made us see how changing the batch size affected the accuracy of our model, and we found out that it decreased it by 1.5%. But we were then able to compensate this because after the model generated the files that it needed, we were then able to increase the batch size to 2 and train future models with the batch size of 2 and the validation data set included. So as you can see here are the two different graphs of using the batch size 2 and the batch size 1. Finally, our model now, our curves have the training accuracy and the validation accuracy and the validation loss and training loss, so that we can compare them together and see if overfitting exists. And as we can see, we started to notice that our model is actually overfitting from the loss graphs here. Not that significant, but there was some overfitting that we decided that we might propose to solve.
So after training the model using the L2 regularizers that was used in the baseline model, we found these plots. We achieved an accuracy of 83%, but if we look at the plot loss, we can see the huge generalization gap between the validation loss and the training loss, which means that there is overfitting in this model. And this is clear from the model is doing well in the training dataset, but it's doing bad in the validation dataset. So we try to avoid this overfitting by changing other hyperparameters, as we will see. So at first we replace the L2 regularizer by L1 L2 regularizer, and as we see from the loss plot, it reduces the overfitting, and the generalization gap between the validation training is very small now, and but the accuracy reduced by 1%. But after using L1 regularizer instead of the other two, we have achieved the same accuracy of 83%, and now there is no overfitting in the model.
Okay, then we decided when we looked at our code, we found out that our model uses a segmentation model of version Deep Lab version 3. There we found that there includes different models from this exact Deep Lab version 3. And so we decided to try different variants from them that we found online. So we tried a different Deep Lab version 3 that was based on the exception architecture. We found the pre-trained weights online, and we downloaded it and included it in our code. And we found out that it yielded very similar results, but caused a decrease of 1% in accuracy. So we decided that we are going to continue forward with the original Deep Lab version 3 weights and model that was recommended by the researchers that published the original model. We then decided to try different optimizers. We first tried the initial paper, or the initial model uses Adam regularizar, and as we can see, it causes an accuracy of 83% in this run. We then tried to use different regularizers like the SGD, and we found out that it significantly dropped the accuracy of the model and caused huge overfitting, as can be noticed here from the graphs. So it dropped the accuracy to 58.6%, which is close to guessing, so it's not a good solution. Then we tried the RMS prop optimizer, and we found out that it caused almost identical results to the Adam optimizer, causing an accuracy of 82.9%, which is not a significant difference from the Adam optimizer. So we decided to continue again with the Adam optimizer.
So to wrap up the differences between our current model and the original model, now we are using LSTM instead of Jeru for the RNN architecture. And regarding the train segmentation model, we have unchanged the Deep Lab V3 model that uses the baseline model. We also now are using L1 instead of L2 regularizar. And for the optimizer, we stays with Adam. And regarding the validation, now we have a validation history for accuracy and loss is now available for overfitting check.
Okay, as for the next steps, we finally, after looking through the 6,000 or 7,000 lines of code that we have for our model, we finally detected where is the VGG19 model included, since our code initially has a configuration file that supposedly editing in it should change this VGG19, but we found out by experimenting that this is not the case. So we finally found out where the VGG19 is hard-coded in the code. So in the next milestone, inshallah, we are going to be able to optimize this and change it to try different models, different newer models and different newer architectures to reach, inshallah, higher accuracy. So we are going to try the ResNet, the Inception ResNet v2, Inception v3, and Exception model. We are also going to tune and test different hyper parameters that are included in our model, including the depth of the model itself by trying to add different layers, or in changing the weights of the dropout layer, or even trying to change the learning rates.
So here is the team contribution for me and Mohammed, and here is the references, and thanks.
Thank you.